So we already talked about the atom on chapter 2, and we say the atom was made of different particles, protons, neutrons, electrons. Protons you cannot change because you change the identity of the atom. Isotopes you can change because some atoms have more neutrons than others, and because of those variants, we call them isotopes. And we use the isotopes to determine the atomic mass of the atom. Then we have the electrons. Electrons you can touch, and if you change the number of electrons, you get negative and positive atoms because that unbalance of charges. But electrons are more important than they seem to be because electrons determine the properties of the atom. It determines how those elements are going to behave. And what we are going to do today, we are going to see a few patterns emerge. And there's a few things you are going to have to memorize because you will not have them available in the test, but they're very straightforward and easy to do if you learn how to do them. So before we do anything, we are going to start by talking about the spectrum of magnetic energy because we are going to use this to describe what's happening in the atom. So we have a spectrum of wavelength and frequencies where we have our gamma rays, our S rays, ultraviolet light, infrared light, microwaves, and so on. The higher the frequency, the more dangerous those rays are. So gamma rays are the most dangerous ones. S rays are not, well, they're still dangerous in large amounts, and that's why when you go and have your S ray taken, they put a lead mantle on top of you so the parts of your body don't get it too much S rays if they don't need to. And then we have this very narrow region of frequency where the visible light happens. So we look at light, we see it's white, but is light really white? What do you think? I'm not trying to be philosophical in here, and it looks white, but it isn't really white. Light is made of all the different colors. And it's a very narrow region of frequency where that happens. Everything else we cannot see. Being able to understand that we have a region where we can see different colors. Lower frequencies are towards the red, higher frequencies are towards the blues. So when we have an atom, we kind of know from what we've done in the past, that the atom has a center where the nucleus is, and then we have these orbits where the electrons are located. So sometimes the atom is just hanging around, and all of a sudden, this burst of energy hits one of the electrons. So we have this incoming photon of energy. Is that electron? The electron gets hyper. It has too much energy now. So what is it going to do? It's going to jump up. It gets excited and jumps to a higher energy level. Now it's hanging up there with a lot of energy. That energy starts wearing down, and you know what? I don't like it up here. I'm going to jump back down. So it jumps back down. As it jumps back down, whatever energy has left is emitted out. That energy that's emitted out is the energy that we can see in that region of frequencies. It's going to have a very specific value. So this whole thing is a four-step process. You have the electron absorbing energy, then jumping up because it gets excited, then it jumps back down, and as it jumps back down, releases energy. That energy release is the energy that we can see as a color, and it's very specific. There's only a couple things I want to mention here, and that is that energy is quantized. What that means is it has a very specific value. When you come up the elevator versus the stairs, when you come in the elevator, as the elevator is going up, depending on how you stand in that elevator, you can have a set of energy. That energy can vary because of how the elevator is moving and how you're moving inside that elevator. When you come up the stairs, as you take one step on one of the steps of the stair, that's a specific energy. When you go to the second step, another energy, and so on. So each step has a specific value of energy. That's what we say is quantized. Unquantized means it could have different values. You end up in the same place, but understanding that energy is quantized is important because each one of these orbits will have a very specific value of energy. Okay, so why is this all important? Why am I talking about energies? Why am I talking about the quantized? Why am I talking about color? Well, the reason is because each single element in that periodic table has a very specific pattern of energies where those electrons are jumping up and down. Each element emits a very specific spectrum. If we took light, light is just a continuous spectrum. It has all the colors. When you take an element like neon, neon is going to be producing very specific lines of colors. And you can see that this in real life. You can take a spectrophotometer. It's like a prism that you look through a light. And the way we do it is we take these tubes of different elements. It's just a gas inside a glass tube that is in a vacuum. And when you apply a voltage to both ends, the electrons of that element are going to start jumping up and down. When they start jumping up and down, you can see the energies of those electrons that are being released as very specific colors. The more lines, the more electrons that atom has. And because every element in the periodic table has a very specific spectrum, if we can identify the spectrum of that element, we know what element we are talking about. In Roman times, Romans used bromine to attack their enemies. They did that because bromine will kill as a gas because it's very toxic. They didn't know what bromine was. So every element has a very specific spectrum, and that spectrum is generated from those electrons jumping up and down. The more electrons you have jumping up and down, the more color lines they have. And the intensity and the location also depends where those electrons are jumping from. If they're jumping from an orbit number 1 to an orbit number 4 and then down, that energy is going to be different from jumping from 1 to 3 and down. So how big that jump is has also an effect on the intensity and the amount of those lights. Okay, let's move on. Okay, so now let's summarize this a little bit. So we know the electron, we know the atom has these orbits. That's what we call the Bohr model because of Niels Bohr, a scientist. He said that electrons are like planets in straight 2D orbital orbits, circular orbits. The more electrons, the more orbits you have around that nucleus. But that's really not what's going on. After further and further studies, we know that the atom doesn't really look like that. The atom, or the modern model, what we call the quantum model, is just a cloud of electrons. So the electrons are no longer in orbits. The electrons are moving around the nucleus in certain patterns, and we use probabilities to describe the most probable location of those electrons. And that's why we call it a quantum model, because we use quantum numbers to describe the location of all those electrons. And that's based on Schrödinger. You probably heard about Schrödinger cat. That's all based on quantum mechanics. Quantum mechanics is a part of chemistry that's very complex. It's not something that you really do by hand. You use supercomputers to do all these calculations, and here's the problem. Once you finish the calculation to determine where one electron is, you have to start all over, because that electron will move to a new position. Remember, electrons are not standing still, they're always moving. Therefore, the location of the electron is better described as a probability. The denser the cloud, the more probable that electron will be there. The lighter the density, the less probable that electron will be there. So now we have this model that describes better how the atom looks like. And that description is going to help us come up with a way of describing how all those electrons are located in that atom. We are going to come out with like an address that we can use to predict where every electron will be located in the atom. So if we have 10 electrons, there will be the address for 10 electrons. And we're going to look at that address like, okay, I'm going to a game. I know which section of the park I'm going to go. I know which subsection I'm going to find my seat. I know the row. I know the seat number I'm going to be sitting. So it's basically the same thing that we're going to do here. So we are going to use a set of quantum numbers. And after I go do this, we are going to do it one more time, but we're going to do it step by step so you see how it's done. The first quantum number, there's a set of 4 numbers. The first one is what we call the principal energy level, N. This first quantum number refers to the energy and the distance of the electron to the nucleus. The bigger the value of the level, the bigger the atom. So an atom with a level 1 is smaller than an atom with a level 4. And an atom with a level 4 is bigger than an atom in level 1. So N goes from 1 to infinity. Lucky for us, we don't have to go to infinity with this. N is going to go all the way to 7, and that's it. So from 1, for all purposes, it goes from 1 to 7. Let me ask you this, why only to 7? Let's see if you can. Because of the periods of the periodic table. It's only 7 periods. So that principal energy level and not only tells you the energy associated with that level, how big that atom is, it also tells you the location in the periodic table because it tells you what period that electron will be located at. So that's the first quantum number. The second quantum number, which is the sublevel, the second number refers to the sublevel. So within that level, there's many sublevels. So it tells you the type of level or sublevel you have. And those sublevels, we're going to use letters to describe them. And those letters are S, P, D, and F. There's only 4 letters. And that's also because of how many elements we have in the periodic table. We don't need more than 4 letters. In the case that we'll need more letters, we'll just keep going with the letters that come after the F. So that will be G and so on. But S, P, D, F are letters for now. So first quantum number, the level or the orbit. Gives you the energy and the size of the atom and the location. Second number tells you the type of sublevels you have within that level. The third quantum number tells you how many of those types you have. So how many S, how many P's, how many D's, how many F's you have. And as we start our next table that we're gonna do, we'll look at how to determine how many of each we have. Okay, so the total number of electrons in any energy level follows the formula 2n squared. The n is the level. So if you are in a level number 1, 1 squared is 1 times 2, you can only have 2 electrons. If you are in a level 2, that's 2 squared, that's 4 times 2, that's 8. The third is 9 times 2 is 18, and then 36. Good? I know right now it looks, okay, how am I gonna do this? This is kind of confusing. It is not, you'll see. Trust the process. Before we do that, those different type of orbitals look like this. The s orbital are just a sphere. That sphere, there's only one of those. So the s is only one type. For the p, it's like a dumbbell that can go in the z, x, or y axis. So there's 3 of those. The d gets more complex because it's a double lobe. It's like a clover. It's more complex. There's 5 of those. And the F, there's 7. Why 5, why 7, why 3? Because in a 3D spectrum, a 3D space, you can rotate those suborbitals in different directions. And it happens that for the P, you can do it in 3 different directions. For the D, you can do it in 5 different directions. And the F, you can do it in 7 different directions. We are not going to investigate how those locations look like. That's a much higher level chem. Just know that for the S, there's only 1. For the P, there's 3. For the D, there's 5. For the F, is 7. That's going to become handy very soon. Alrighty. Okay, so let's do this table. So we are gonna do N, then the sublevel, then the orbital. I'm only going to do it for the first 4 just to keep it simple. So if N equals 1, how many electrons can I put there? How many did I say? 2. The sublevel, we always start with the S. So we're gonna have an S sublevel there. I already said there's only 1, right? So that means that for an S sublevel, I can have 2 electrons in that sublevel. So each sublevel type can hold a maximum of 2 electrons. There's only one S, it can hold up to 2. There's only one of those. Then we move on to level number 2. The level 2 can hold up to how many total? If you forgot, you can use that 2n squared. So if n equals 2, that's 2 squared, that's 4, times 2, that's 8 total, right? I know in the S I can put 2. Then comes the P. I can put up to 6, which I already told you. When I add 6 plus 2, that gives me the 8. So there's only one S type. How many P's then? There's more than one. How many electrons per sub level? 2. I have 6. How many types? 3. Then we have the level 3. So we have 3 squares 9 times 2, that's 18. So we have the S, P, D, that's 2, that's 6. So this one has to be 10. There's one S, there's 3 P's. How many D's then? 5. Because you have 10 electrons, 2 per sublevel, so I did 5 of those. So 5 times 2 is 10. And then we have level 4. So we have 36. So we have S, P, D, and F. So it's 2, that's 6, that's 10. This one has to be 14. So that's 1, 3, 5, and 7. When you add all the electrons from each of one of those sublevels, you get that 36. At those, you get the 18. At those, you get 8. That's just 2. You will have questions like this. How many sublevels in a level number 3? So you have 2S, you have 1S, 3Ps, and 5Ds. Knowing how many sublevels is critical, is important for where we are heading. And we're getting very, very close to where we are going to start using all this. If you're taking chemistry before, you've probably seen this already. The only difference is that it's being given to you in a very simplified way. It's being given to you by the letters without explaining where those letters come from, where a lot of all these things apply. So let's move on. We're going to leave that table there for now, and then we're just going to define these 3 rules. And we need these 3 rules for what? So we can describe the location of those electrons. The first rule is the Aufbau principle. You start feeling sublevels starting with the lowest energy. How do you know which one is the lowest energy? It is the one with the lowest energy level. Remember, lower energy level, lower energy. So lower N, lower energy. Then you have this Pauli exclusion principle. You have 2 electrons per orbital or sublevel. They must have opposite spins. We'll revisit that statement soon. And then we have Hund's rule. In equal energy orbitals, each box will be filled with 1 electron at a time in the same direction before they're paired up. This makes no sense for us right now. It will very soon. And I'll point out these rules as we start using them, because I believe what's coming now. I'll hold on in here for a second. So let's do this thing called orbital diagrams. Orbital diagram shows the electrons for each element inside boxes, and we are going to use arrows to represent those electrons. So we always start with a 1s. So hydrogen only has one electron. So we can only use one arrow. So I'm just going to say, okay, that arrow is going to go up. I'm just going to put one arrow in there. If I were to do helium, helium has how many electrons? 2. It's still 1s because I can put up to 2 in a 1s. Because it's s, you can put up to 2. So we already know that the first electron is going up. So the second electron has to go down. This is a convention that we use. If I start with the arrow going down, the second one has to go up. So in each box, those arrows have to go in opposite directions because of Hund's rule. So Hund's rule, single arrows fill boxes before doubling up, and when they double up, one goes up, the other one goes down. If I do nitrogen, nitrogen has 7 electrons. So we start with a 1s, up, down, that's 2, 2s, up, down, that gives me 4. Then from the 2s, we're going to jump to the 2p. Because it's a p, I have 3 different possibilities. I have 3 electrons left in nitrogen because it's 7, and that's 4 already. 5, 6, 7. I put 1 in each box before I pair them up. And that's based on the rules we just explained. And then oxygen has 8. So if this is 7, I just add 1 more, but going in the opposite direction to get the 8. So orbital diagrams just show us the electrons per sublevels. Okay, I just gave you the arrangement that we're going to use. So it's saying it's 1s, 2s, then 2p, and so on. But how do we determine the sequence we are going to use? We are going to do that by using this diagram that I have here on the left. That diagram is called the Aufbau diagram. You need to remember how to do this diagram because you are not going to have it in the test. So we always start at the top. N equals 1, then N equals 2, 3, 4, 5, 6, 7. I threw 8 in there. Then if N is 1, we know the number 1 refers to the level, and we only have the S from the table we just did. For N equals 2, I'm going to have a 2S and a 2P, because we can have S and P sublevels. And then for N3, we have S, P, and D. For the 4 is S, P, D, and F. The same for the 5, 6, 7, and 8. For the 6, 7, and 8, I'm omitting some of those because we don't really need them. And the reason we don't really need them is because of elements in the periodic table. Not all of them will fill those sublevels. So the way this diagram works, you are going to draw diagonal lines going down from the top, the way they're written there. Then the head of one connects to the tail of the other one. And so on. So when I start at the lowest energy level on top, which is the 1s, I just follow the arrow. So 1s is followed by the 2s, 2s is followed by the 2p, and then the 3s. Then this should be 3p here. So 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and so on. So this diagram gives you the sequence you need to use to generate what we're going to call electronic configuration. An electronic configuration gives you the location of all the electrons in the atom. They do much more than just that, because n equals 1, that's period number 1, and 2 is period number 2, and so on. So when we get to n equals 7, that's period number 7. Just remember that the last two rows at the bottom of the periodic table are embedded in period 6 and 7 of that periodic table. They're just out at the bottom, so there's enough space to have all the elements in one 8x11 page. So we have hydrogen, we start on the top. Hydrogen has only one electron, so 1s1. Oxygen has 8, so 2 in this one, that's 2. In that one, that's 4. And the P, that's 3. 3, 4. So 2, 4, and 4, that's 8. Aluminum is going to do the same thing. Now, let's look at copper down here. Ignore what is written right there. If I'm going to write for copper, how many electrons for copper? 29? 29. So we start with the 1s2, 2s2, 2p6, 3s2, 3p6. Let's see how many that is so far. That's 10. That's 18. After 3p comes 4s. So it should be a 3p here. I can put up to 2 there, right? So that's 10 and 10, that's 20. So in here should be a 3d 9. But that's not how we write the configuration for copper. This is how we write it. We write it as a 4s1 3d10 instead of a 4s2 3d9. Let me do this in here. So the way it's written at the bottom, you have 2 in here, and then 1, 2, 3, 4, 5, 6, 7, 8, and 9. What I'm telling you, that's not how we do it. The whole idea here is the electronic configuration gives you the most stable location of all those electrons. So there has to be something about this one that's not preferred compared to the other one. Because the other one is like that. What's the difference in one versus the other? Just one electron, right? Okay, so why is this preferred and not this? It's most stable. Why? The valence electrons is the last orbit. I haven't talked about valence electrons yet. Is it transition metal? No, we haven't talked about that yet either. And that is, let's compare a couple of elements. Let's do oxygen versus sulfur. Oxygen, we already say is 1s2, 2s2, 2p4. Sulfur has how many electrons? 16. So let's see. 1s2, 2s2, 2p6, 3s2, 3p. How many will that p have? How to know? The top numbers give you the number of electrons. So 2 plus 2 is 4, plus 6 is 10, plus 2, 12. So I need 4 more. So the ending of the first one, 2s, 2p4, sulfur is 3s, 3p4. When we look at oxygen, let me just the 2s2, 2p4 are in the highest energy level because the level is 2, there's 6 in there. For sulfur, the highest energy level is 3, and there's 6 electrons in the 3. So electrons in the highest energy level are your valence electrons. And now we can talk about valence electrons. Okay, so if I were to look at selenium, because it comes after S coming down in the periodic table, that one will end up in 4s2, 3, 4p6, 4p4. And that's the other thing I'm going to mention here. All elements in the same column behave the same way. So they behave the same way, so they have the same number of valence electrons. So does that mean that I have to write electronic configuration for every single element to determine how many valence electrons they have? Why not? You know I'm going to follow up with another question. The answer is, in theory, yes. But us chemists, we like simplifying things. So let's say this is my periodic table. So that's oxygen, that's sulfur, that's selenium. I already know they have sets. What column number is that? If you look at the periodic table, it's not going to tell you. So you have to count from the left. 16. So if I am in column 16, I have 6 valence electrons. So I look at the last number in the column number. If you do it from 1 to 18, I recall that I also told you it's 1A, 2A, 3A, 4A, 5A, 6A. So this is also a 6A. So the column number tells you how many valence electrons you have. So if I am in column 17, I will have how many? 7. If I'm in column 8, I will have 8. If I'm in column 1, it's 1. If I'm in column 2, it is 2. So I can look at the column in which I am located. It tells me how many valence electrons I have. You need to know how to do that because when we start working on bonding next week, bonding is all about valence electrons. Valence electrons are the ones that determine the properties of the element because they are the ones that are going to react because they are the farthest away from the nucleus. They're easier to either remove or add to them. Okay, so that takes care of, we have kind of done orbital configurations, we've done valence electrons, we've done electronic configurations. So now we have those electronic configurations that are kind of long. Let's condense that. Let's make them shorter. To create condensed configurations, we are going to use noble gases that come before the element. So if we are talking about oxygen, the noble gas that comes before oxygen is helium. So let me show you how is that derived in there. So if we have oxygen, was 1s2, 2s2, 2p4. Helium, we are going to use a noble gas before oxygen, which is helium. Helium has 2 electrons, which are those 2. So I'm going to write helium in brackets, and then the leftover, I write down there. Because by doing that, I'm showing that those are my valence electrons. And helium shortest out whatever I have before that. Let's do one that's not there. Let's do calcium. How many electrons? 20? So 1s2, 2s2, 2p6, 3s1, 2p4. 3s2, 3p6, 4s2.